Olan. I'm here with Raoul. He is one of the formal verification engineers at Runtime Verification. And today we're going to talk about what that is. So before we get started, why don't you just share a little bit about yourself? How did you get into blockchain, crypto?
Yeah, thanks, Paul. My name is Raoul, former verification engineer at Runtime Verification. I spent like thousands of hours reviewing smart contracts, DeFi protocols, and now I'm the tech lead of Symbolic, which is our Solidity debugger with symbolic execution built into. How did I first come into blockchain? I think my first transaction that I ever made was back in 2015, before the DAO hack, and I invested a bit of money into the DAO, and then it got hacked. So that was a pain point for me, and I was like, "Hey, we need to find a better way to do that, a more secure way to do that." And yeah, kind of you can think of my biography as a personal revenge story.
So that's a really cool story, actually. So were you on the side for the fork or against the fork?
At the time, I barely had an idea of what I was doing. And that was amplified by how the UX back in the days was for Ethereum. I remember I had to put up my own node, my own full node back then, just to make a transaction. I was in favor of the fork back then just because I wanted to get my money back.
That's fair. That's very fair, right? I love hearing these stories. But let's jump into formal methods. So as I understand them, it's like attempting to confirm that a program adheres to certain specifications for like all possible inputs within reason. So now in like a blockchain example, if a smart contract function takes in an address as one of the inputs, like that's already way more inputs that we could possibly try, right? It's like it would take 20,000 years or something to try all addresses, and that's just one of the inputs. So how do we do it? So that's where symbolic execution comes in, right? Like, can you explain it a little bit better? Because I'm probably not doing a very good job of explaining this right now.
Yeah, but you have a really good intuitive understanding. So there are different security techniques that you can apply to a code base that are automated or more manual. And you usually start with unit testing and then expand into property testing. And from property testing, you expand into symbolic execution. So, and the example with addresses is a very good example because I sometimes get the feeling people don't really understand how big the possible input space of your smart contracts are. So an address in the EVM is 2 to the power of 160. A uint is 2 to the power of 256. And if you would just want to test your smart contract on all possible inputs, and just like let's take one address as an example, or one uint 256 data type, then you would literally need more time than we have left in the universe. Even if you think you could parallelize this, well, you would need more atoms in the universe just to build the hardware to parallelize that at scale, just to test, to fully explore the input space of a function that takes a single uint data type. So, and that is where symbolic execution comes in. So when you have unit tests, you usually test some concrete input values. When you have fuzzing tests or property tests, you generate random parameters and test your function on these random parameters. Now, symbolic execution is the promise that we can test your entire input space. And that, of course, means, well, we need to do it in a very clever way. We cannot just throw all the possible inputs at your smart contract because for the reason that we just explained. And that's why we do what we call symbolically. So instead of calling your contract with specific inputs, we leave these inputs as variables. And then we execute through the code and we code information about these variables and see what are the branches that are actually reachable from your initial state, what are the branches that are not reachable. And then we try to arrive at a conclusion for really all possible inputs. And that's really, really strong correctness guarantee that goes way beyond what traditional testing methods can offer.
Okay, so let me try to paraphrase what you just explained because I mean you did a very good job, but let me see if I understand it. So like you will try to branch off into different variables. So like every time there's like an if statement within the code, that will kind of create two different branches. Is that kind of like a good way to think about it?
Yeah, that's a good way to think about it. So when you have when you don't make any assumptions about the concrete values that a parameter that a variable can take, then you will run into if statements and you will see a condition and you cannot decide at this point, hey, is this condition true or is it false? Because, well, you don't have enough knowledge about your variables. So what you do instead is you branch your execution into two different branches. And then for the one branch, you just assume that the if condition is satisfied. And for the other branch, you assume the opposite, that the condition is not satisfied. So you get 100% coverage of these branches. And the same is true, for example, for loops. If you have a loop, then you don't know when it's going to terminate, if it's going to terminate. When we're testing loops, you would have a zillion of possible execution paths. That is, hey, what if the loop takes one iteration? What if the loop takes two iterations? What if the loop takes three iterations? And so on. And this could expand forever. So we also need some clever way of identifying how we can handle loops in a user-friendly way.
Right. So it sounds like a loop would make this a very time-consuming process, right?
Yeah, it is. I think that's one of the key differences between the symbolic execution tools we develop at runtime verification and other tools in the market. What most symbolic execution engines do is they just give up on this problem and they say, okay, we assume that this loop is at maximum going to iterate 3 times, 2 times, 1 time. But if you have a bug or a vulnerability that only shows if your loop iterates 5 times, for example, then then most of the tools will just not find this bug. And with KVM, Kontrol and Symbolic, we actually have a way of specifying what we call loop invariants. And these loop invariants are like a shortcut to basically subsume all possible loop iterations into a closed formula. And I don't want to go too technical in here, but one of the key differences that sets runtime verifications tooling apart is that we actually can reason about loops time efficiently without cutting off reachable states.
Wow, that's really cool. So how effective is this stuff? Like, can you actually get to 100% coverage or like, is it 99.9, 99%, 95%? Like, what's a good way to quantify it?
So when you look at classical testing tools and what metrics they offer to measure the quality of the test suite is they look, for example, at lines of code covered. They look at they look at how many branches are covered, but they don't look really at input coverage, which I think is a more suitable measurement. So with input coverage, we mean you don't look at the lines of code that you covered, but you look at how much space of your possible input range is covered, of your input domain. So we had this example with addresses and UN256. So, and what symbolic execution is really, it can guarantee you 100% input coverage. And if you look at traditional tools like fuzzing, you can probably get 0.0001% input coverage for reasonable complex smart contracts. But even input coverage is not perfect. The other dimension, and that is, well, harder to quantify, is, well, how good is your specification? How much properties invariants are actually covered by your specification? So you can get at 100% input coverage, but if your specification is just underspecified and misses an important property, then you can get 100% input coverage and you can still have a bug in it. So
right,
quantifying how good your specification is actually, it's a much harder problem to solve.
Wow. So obviously, yeah, specification will be very subjective, but you can actually get to 100% coverage for inputs with using our methods. That's awesome. So let's bring this back down to earth a little bit. Like, what kind of protocols do you think benefit the most out of, going beyond just property testing and fuzzing and actually taking the formal verification step?
If your protocol handles money and it handles money from investors that's not your own, then you definitely want to be as secure as possible. Well, we need to make formal methods more accessible and establish them as a best practice for all the protocols that handle that handle user stakes and where users take a significant risk.
Okay. So, what are some real life examples of bugs you found specifically using formal verification tools?
Yeah, that's a good question. So my favorite example is in one-time verification, we formally verified the deposit contract of the beacon chain. So when Ethereum made the change from proof of work to proof of stake, they developed this deposit contract where potential stakers can come in and deposit 32 ETH and then register themselves basically as a validator. So, and we formally verified this, the first draft of the deposit contract, and there was a subtle bug that was really hard to catch, and I would say it was almost impossible to catch with classical techniques. So there was a bug actually in the Viper compiler. So the first version of the deposit contract was actually written in Viper, not in Solidity, and there was a compiler bug that failed to validate the inputs correctly. So, and that could lead to users staking their money, but not being registered properly. So they would just lose their 32 ETH. And yeah, this bug is a prime example of where formal verifications really shines because, first of all, it was a bug that you would probably miss with classical tooling. Because, for example, if you have a fuzzer or unit testing framework, these frameworks usually, these test suites usually only generate correct input data. But the problem here was that the input data could be malformed. And this is usually something that is not covered by traditional testing tools. So the other part is it would be really hard to find this bug with a classical manual code review, because usually when you do a classical review, you look at the source code. You try to make sense of the Viper code or of the Solidity code, but you usually don't go full into the bytecode level. But this is a bug that existed at the bytecode level, so it was only possible to spot it there. Yeah, that's my favorite example. But
Cool.
if you're interested in more examples, then most of our formal verification reports and also manual audit reports, they are available online. So you can go to github.com/runtime verification/publications and just browse through our formal verification reports.
Awesome. Yeah, we'll include the link to that. And so who ordered that review for the beacon chain? Was it the Ethereum Foundation, or is that something we did to test our tooling?
Oh, the Ethereum Foundation developed this deposit contract, and then they reached out to runtime verification to conduct the formal verification.
Okay. Cool. So, do you think that formal verification could replace manual code review at some point in the future?
Not in the near future. Formal verification tools can offer you really high correctness guarantees, but they are only as good as the formal specification that you have. Well, we have this tool which is called Kontrol, and it's a symbolic execution or symbolic testing framework that is built on top of Foundry. So we actually encourage users to develop a solid Foundry test suite, which doubles as a specification then for Kontrol. So, and you usually what you want to do is you want to first run this Foundry test suite and fuzz heavily over it, harvest all the low-hanging fruits, and then once your Foundry test suite is passing and is showing a green check mark, you want to take this test suite and feed it into Kontrol just to hammer out all the possible edge cases.
That's consistent with what I thought. I mean, it seems like formal verification is kind of the next step in the evolution of our security toolkit, right? It's probably a nice way to put it. So, what are some important downsides of formal verification? I think we already kind of touched on it has to be, the specification has to be really good. Otherwise, it won't do that much for you. And then we also kind of touched on it's a little bit compute intensive, right? Um, what else? What are some downsides to trying to get into formal methods? And
We currently have a problem with the accessibility of these tools. So most formal verification projects come straight from academia. They have been invented at a research lab, and they don't care that much about developer experience. So if you compare, for example, using the formal verification tools that exist today to the developer experience of classical testing tools like Foundry, then you would have a much easier time picking up Foundry. So developer experience is the most hampering reason that we don't see broad adoption for formal verification. It has become much easier during the recent years. So if you look at the integration that Halmosh and Kontrol offer with Foundry, you can just reuse your existing test suite and now use symbolic execution tools on top of what already exists in your code base. You don't have to learn a new specification format. So we talked about like how formal verification tools always like they basically get two inputs. The first one is the code base. The second one is the formal specification. And traditionally, it has been that the formal specification has been needed to be written in a custom specification language that would look really weird and foreign to ecosystem. So, but now we are seeing, hey, we can use Solidity as our specification language, which also reduces the risk of subtle misunderstandings because, well, if you have a specification language that maybe looks a bit like Solidity but is not Solidity, then well, there could be things lost in translation, and you could oversee things. So, and that's where I think the newest generation of formal methods tools has done a great job in becoming more user friendly. Also with Symbolic, which is the tool that I'm working on at Runtime Verification, we found a good visual metaphor to explain symbolic execution to devs who do not have a college degree in formal methods. So the story here is Symbolic is a Solidity debugger. So, and you can just use it as a concrete Solidity debugger. You can set breakpoints, you can set variables. So debuggers usually that people also from the devs from other ecosystem are already familiar with. So, and now on top of this concrete debugger, we also offer now symbolic execution features, which means it becomes only a small step from using a debugger to becoming a symbolic execution expert. And the nice thing here is you don't need to be a college graduate. You can just build on your existing experience with debuggers and then gradually evolve more into symbolic execution as you learn more about how it works internally.
Okay, so you covered a lot of what I was just about to ask you about Kontrol and Symbolic. So these two tools, pretty much any Solidity developer could pick up and start experimenting with formal verification without having to learn a new language or like new semantics, right? And are these tools free to use? How do developers find them?
Yeah. So most of our tools at Runtime Verification, they are open source or they are going to be open source. So for Kontrol, Kontrol has been in the market for over a year now, and it's fully open source. It's built on top of KVM, which is also fully open source. And KVM has been around since 2019. So it's a pretty major symbolic execution engine. Yeah, you can go to control.runtimeverification.com to get on the landing page of Kontrol. There you will find the download link. You will find the instructions, the documentation. Symbolic is in a more early development stage. So at the moment we are running a closed beta version where some signed up beta testers have access. But we are now working on doing an open beta version.
Okay. So yeah, so if there's one thing that the viewers should walk away with is try Control, try Symbolic. I mean, I'm a hobby level Solidity tinker, and I was able to, clone a code base, run Control, try to do some tests on my own. Some of that is still rough around the edges, but like it just works out of the box, and it's pretty incredible, powerful stuff. Um, so for those who are seeking the highest possible security assurances for their protocols, and maybe they're too intimidated to just start running formal verification on their own, runtime verification can come in and help them audit end to end, formally verify their contracts, right? Do you want to talk a little bit about what engagements like that look like, and encourage people to do them and secure our ecosystem?
We try to think security as a package. So we offer services like for any stage and any protocol. Like if you just have a design but have no implementation yet, you can come to us and ask us for advice on, for example, the economical incentives. Are they aligned? Are there any economical attack vectors? Then we have the classical code reviews. And what we are also seeing more is demand for developer teams who want to run their own formal methods. They want to run their own formal verification tools. And they can do that with Control, and they can do that with Symbolic. For developer teams, usually that means they come to runtime verification, and we basically help them get up to speed with our tooling. So, for example, Control has a very nice feature that lets developer teams integrate Control into their CI pipeline, and then with every code change, you can run your symbolic execution test suite again and again. And that's basically, once you have the specification, running it again on your CI becomes a no-brainer. And we also help developer teams to write good specifications and get these specifications ready to be executed with Foundry, to be executed with Control.
All right, awesome. I think that's all the questions that I had for you today. Thanks for teaching me about formal methods, and hopefully we get some more developers signing up for Symbolic beta, and hopefully we release the alpha version soon.
Yeah. Thank you for having me, Paul.
All right. Good talking to you. Take care.
Take care.